Dark matter. Dark matter constitutes one of the most profound enigmas in modern physics and cosmology, an invisible scaffold, shaping the universe's structure while eluding direct detection. Its significance lies not merely in mass accounting, but in its pivotal role in galaxy formation, cosmic evolution, and the dynamics of large-scale structures. Despite its inferred ubiquity, the true nature of dark matter remains a central, unresolved question, challenging our understanding of fundamental particles and forces. The concept traces back to early 20th century observations, when discrepancies emerged between visible matter and the gravitational behavior of galaxies. Pioneering astronomers like Fritz Zwicky, who studied galaxy clusters in the 1930s, first suggested the presence of missing mass, while Vera Rubin's rotation curves in the 1970s confirmed anomalous galactic motions consolidating dark matter as a critical cosmological component. Over decades, theoretical models evolved, gradually shifting from speculative ideas to systematically constrained frameworks. Dark matter is characterized as non-luminous and weakly interacting with electromagnetic forces detected primarily through gravitational effects. Its underlying physics involves mass energy contributions to space-time curvature, influencing galaxy rotation, gravitational lensing, and cosmic microwave background anisotropies. Related phenomena include halo formation around galaxies and the emergence of large-scale cosmic web structures. Current theories encompass particle-based candidates like WIMPs, axions, and sterile neutrinos, alongside modifications to gravity, such as MOND. Mathematical models employ quantum field theory, cosmological simulations, and relativistic frameworks, each attempting to reconcile observations with theoretical predictions. Observational evidence spans galactic rotation curves, lensing maps, and cosmic microwave background measurements, though anomalies persist, highlighting tensions in small-scale structure formation. Challenges remain in identifying particle properties, detecting direct interactions, and explaining inconsistencies. Dark matter connects deeply with neutrino physics, dark energy, and the broader quest for a unified theory. Future prospects involve advanced detectors, deep space surveys, and high-precision simulations, promising unprecedented insights into the universe's hidden majority. Ultimately, dark matter represents both a scientific frontier and a philosophical reflection on the limits of human perception and understanding. Dark energy. Dark energy refers to the unknown component of the universe responsible for its accelerating expansion. Discovered through precise cosmological observations, it has reshaped modern cosmology by revealing that the majority of the cosmos is governed by physics not yet understood. Its significance lies in challenging fundamental assumptions about gravity, space, and the ultimate fate of the universe, raising one of the deepest open questions in science. The idea emerged in the late 20th century when astronomers studying distant Type Ia supernovae found that cosmic expansion was speeding up rather than slowing down. Teams led by Saul Perlmutter, Brian Schmidt, and Adam Rees provided the first strong evidence, later supported by measurements of the cosmic microwave background and large-scale galaxy distributions. Over time, dark energy became a central pillar of the standard cosmological model. At its core, dark energy is described as a property of space itself, exerting a repulsive effect that counteracts gravity on cosmic scales. The simplest interpretation is the cosmological constant associated with vacuum energy, though its observed value sharply conflicts with theoretical predictions from quantum physics. Related phenomena include cosmic acceleration and the geometry of spacetime. Current models range from a constant vacuum energy to dynamic fields and modifications of general relativity. Observational evidence comes from supernova surveys, galaxy clustering, and precise background radiation measurements, though subtle tensions persist between datasets. Major challenges include explaining its nature, magnitude, and origin. Dark energy connects to unresolved problems such as quantum gravity and the structure of spacetime. Future missions, improved telescopes, and new theories may offer breakthroughs. Until then, dark energy remains a profound reminder of how much of the universe lies beyond current understanding, inviting deeper inquiry and philosophical reflection. Accelerating expansion of the universe. The accelerating expansion of the universe refers to the observation that cosmic space is not merely growing, but doing so at an increasing rate. This discovery reshaped modern cosmology, forcing physics to confront phenomena beyond gravity as traditionally understood. It strikes at the heart of how the universe began, how it evolves, and how it may ultimately end, while raising profound questions about the nature of reality itself. Early cosmological models assumed that cosmic expansion should gradually slow under gravity. This view began to change in the late 20th century through observations of distant Type Ia supernovae, led by scientists such as Saul Perlmutter, Brian Schmidt, and Adam Rees. Their measurements revealed that distant galaxies were receding faster than expected, implying acceleration rather than deceleration. Central to this phenomenon are concepts such as cosmic expansion, dark energy, and the cosmological constant. General relativity allows space itself to stretch, and under certain conditions, this expansion can accelerate. Dark energy is the term given to the unknown agent driving this process, possibly linked to vacuum energy or an intrinsic property of spacetime. Current models are dominated by the lambda cold dark matter framework, where a cosmological constant accounts for acceleration. Alternative ideas include dynamic dark energy fields and modifications to gravity itself, each attempting to explain observations through different mathematical foundations. Evidence comes from supernova surveys, cosmic microwave background measurements, and large-scale galaxy distributions. While these largely agree, tensions remain, particularly in precise expansion rates. Unresolved questions persist. What dark energy truly is, why its strength has its observed value, and whether current theories are incomplete. These mysteries connect to quantum physics, gravity, and the ultimate fate of the cosmos. Future missions, improved telescopes, and refined theories promise deeper insight. Understanding cosmic acceleration may not only explain expansion but redefine our place in an evolving universe. Before the Big Bang. The question of what existed before the Big Bang sits at the frontier of modern cosmology, where physics meets philosophy. It matters because it probes the origin of space, time, and physical law itself, challenging the assumption that the universe has a simple beginning. At its core lies a profound mystery, whether before even has meaning when time itself may have emerged with the cosmos. Early thinking assumed an eternal universe, but Einstein's general relativity revealed a dynamic cosmos. George's lemma tree proposed cosmic expansion, and Edwin Hubble's observations confirmed it. By the mid-20th century, the Big Bang model dominated, yet its equations pointed backward to a singularity where known physics breaks down, forcing scientists to reconsider the notion of an absolute beginning. Key ideas involve spacetime, singularities, quantum fields, and causality. General relativity describes gravity as geometry, while quantum mechanics governs the microscopic. Near the Big Bang, these frameworks collide, implying extreme densities, where quantum gravitational effects cannot be ignored and familiar concepts lose clarity. Modern theories explore alternatives. Quantum gravity approaches, such as loop quantum cosmology, suggest a prior contracting universe and a cosmic bounce. Inflationary and multiverse models envision earlier phases governed by different vacuum states. String theory proposes extra dimensions and pre-Big Bang scenarios driven by fundamental symmetries. Observationally, evidence comes indirectly from the cosmic microwave background, large-scale structure, and primordial fluctuations. While these support early inflation, subtle anomalies leave room for new interpretations. Major challenges remain: singularities, the arrow of time, and untestable regimes. This topic connects to dark energy, black holes, and the unification of forces. Future observatories, gravitational wave probes, and deeper theory may illuminate what, if anything, came before. Until then, the question endures, inviting humility, rigor, and wonder. Matter-antimatter asymmetry. Matter-antimatter asymmetry refers to the striking imbalance between matter and antimatter in the observable universe. According to fundamental physics, the Big Bang should have produced matter and antimatter in equal amounts, yet the cosmos we inhabit is overwhelmingly dominated by matter. This imbalance is not merely a detail. It is the reason stars, galaxies, planets, and life itself exist. Why anything survived at all remains one of the deepest puzzles in cosmology. The roots of this question trace back to early 20th century physics, when antimatter was first predicted by Paul Dirac and later confirmed experimentally. Discoveries such as CP violation in the mid-1960s hinted that nature treats matter and antimatter slightly differently. Over decades, increasingly precise experiments have refined this insight, while simultaneously revealing how insufficient known effects are to explain the observed imbalance. At its core, the problem involves symmetries, conservation laws, and the conditions of the early universe. Matter and antimatter annihilate when they meet, converting mass into energy. For matter to dominate, certain symmetry-breaking processes must have occurred, allowing a tiny excess of matter to survive. These processes are closely tied to particle interactions, fundamental forces, and the arrow of time. Modern theories propose mechanisms such as baryogenesis and leptogenesis, often extending beyond the standard model of particle physics. Experiments at particle accelerators and observations of the cosmic microwave background provide crucial evidence, though tensions and anomalies persist. Despite progress, major questions remain unanswered, driving active research across theory and experiment. This mystery connects to dark matter, cosmic inflation, and the origin of physical laws. Solving it could reshape our understanding of why the universe exists in its present form, inviting both scientific rigor and philosophical reflection on existence itself. Black hole singularities. Black hole singularities sit at the deepest edge of modern physics, marking points where matter is compressed to infinite density and known physical laws appear to collapse. Their significance lies in the fact that they expose the limits of general relativity and challenge our understanding of space, time, and causality. At the heart of the mystery is whether singularities are real physical entities or signals that current theories are incomplete. The idea emerged from Einstein's general theory of relativity, which predicted gravitational collapse under extreme conditions. Karl Schwarzschild provided the first exact solution describing black holes, while later work by Roger Penrose and Stephen Hawking demonstrated that singularities are unavoidable under broad conditions. Over time, these mathematical curiosities evolved into central objects of study in cosmology. A singularity is defined as a region where curvature becomes infinite and spacetime ceases to be well-defined. Gravity overwhelms all other forces and classical descriptions fail. Phenomena such as event horizons, tidal forces, and spacetime warping are intimately connected to singular behavior. Modern theories attempt to address singularities through quantum gravity frameworks. String theory, loop quantum gravity, and holographic principles propose radically different resolutions from smeared-out cores to information-preserving boundaries. Observationally, singularities are hidden behind event horizons, but indirect evidence comes from gravitational waves, black hole imaging, and stellar dynamics. Some measurements hint at subtle inconsistencies that could point beyond classical theory. Major challenges remain, including the information paradox and the breakdown of predictability. Singularities connect to dark energy, the Big Bang, and the unification of forces. Future progress may arise from next-generation observatories and deeper quantum theories. Ultimately, singularities invite philosophical reflection on whether infinity exists in nature, urging continued exploration of reality's most extreme frontier. White holes. White holes are hypothetical regions of spacetime predicted by the equations of general relativity, often described as the time-reversed counterparts of black holes. While black holes trap everything that crosses their boundary, white holes would allow matter and energy to escape, but never enter. Their significance lies in how they test the limits of gravity, time symmetry, and causality in cosmology. The central mystery is whether white holes can exist in nature or remain purely mathematical artifacts. The idea emerged from early solutions to Einstein's field equations in the early 20th century, particularly the Schwarzschild solution. Scientists such as Carl Schwarzschild and later John Wheeler explored how these equations permit both collapsing and expanding spacetime regions. Over time, understanding shifted from classical interpretations to quantum gravity-inspired perspectives. Their core, white holes, involve event horizons, spacetime singularities, and time reversal. They rely on the same relativistic geometry as black holes, but with inverted boundary conditions. This connects them to wormholes, Hawking radiation, and entropy, raising questions about the arrow of time. Modern theories place white holes within extended black hole solutions, loop quantum gravity models, and speculative cosmological bounce scenarios. Competing hypotheses debate whether quantum effects could transform black holes into white holes using mathematical extensions of spacetime metrics. So far, no direct observations confirm white holes. Astronomical data occasionally reveal high-energy bursts or unexplained emissions, but none conclusively match white hole predictions, leaving inconsistencies unresolved. Major challenges include instability, violation of thermodynamic principles, and lack of empirical evidence. These issues keep white holes at the frontier of theoretical research. White holes connect to black hole evaporation, the origin of the universe, and information paradoxes. If understood, they could reshape ideas about time and cosmic beginnings. Future progress depends on quantum gravity theories, improved observations, and deeper philosophical insight. White holes remain a reminder that the universe may be stranger than imagination allows. Inside black holes. Black holes represent one of the most extreme predictions of modern physics, regions where gravity overwhelms all known forces and spacetime itself is pushed to its limits. They matter not only as cosmic objects but as theoretical laboratories where general relativity and quantum mechanics collide, exposing a deep mystery at the heart of nature. The idea of objects so dense that not even light could escape emerged in the 18th century, but it was Einstein's general theory of relativity that gave black holes a rigorous foundation. Solutions developed by Carl Schwarzschild and later work by Roger Penrose and Stephen Hawking revealed that gravitational collapse leads inevitably to singularities, forcing physicists to rethink the structure of space and time. Inside a black hole, familiar concepts fail. The event horizon marks a boundary beyond which causality is altered, while the singularity represents a breakdown of known physics. Tidal forces, spacetime curvature, and the irreversible flow of time dominate, raising questions about determinism and physical law. Modern theories attempt to describe these regions using quantum gravity, string theory, and holographic principles. Competing models suggest that information may be preserved in subtle ways, challenging classical expectations and reshaping our understanding of entropy and reality. Observationally, direct access to black hole interiors is impossible, yet indirect evidence from gravitational waves and horizon-scale imaging supports theoretical predictions. Still, paradoxes such as information loss remain unresolved. Understanding black hole interiors connects to the origins of the universe, quantum fields, and the nature of reality itself. Future observations and theoretical breakthroughs may reveal, whether spacetime ends, transforms, or encodes, deeper truths within these cosmic abysses, inviting continued exploration of the unknown. Black hole information loss. Black holes sit at the crossroads of gravity, quantum theory, and cosmology. They are extreme objects where known laws of physics collide, making them uniquely significant. At the heart of this topic lies a deep mystery: whether information about matter falling into a black hole is truly destroyed or somehow preserved, challenging our most fundamental assumptions about reality. The puzzle emerged in the 20th century with the development of general relativity and quantum mechanics. Carl Schwarzschild provided the first black hole solution, while later work by Stephen Hawking revealed that black holes emit radiation and can slowly evaporate. Hawking's calculations suggested that this process erases information, igniting decades of debate and reshaping theoretical physics. Information in physics refers to the complete description of a physical system. Quantum theory insists it is conserved, yet black hole evaporation appears to violate this rule. Event horizons, singularities, and Hawking radiation form the core mechanisms driving the paradox, linking gravity, entropy, and thermodynamics in unexpected ways. Several theoretical frameworks attempt to resolve the issue. Black hole complementarity, holography, and the idea that information is encoded on the event horizon offer competing explanations. More radical proposals invoke quantum gravity, spacetime emergence, or subtle correlations hidden in radiation. Direct experimental evidence remains elusive, relying instead on astronomical observations and theoretical consistency. While data from gravitational waves and black hole imaging support general relativity, they do not yet reveal how information behaves at the deepest level. The main challenge lies in unifying quantum mechanics with gravity. Paradoxes persist, and active research continues to probe spacetime, entropy, and quantum entanglement. This problem connects to quantum gravity, the origin of the universe, and the nature of reality itself. Resolving it could redefine space, time, and information. Future insights may arise from advanced observations, theoretical breakthroughs, or a complete theory of quantum gravity. The mystery endures, inviting deeper reflection on what the universe truly remembers. Cosmic inflation. Cosmic inflation is the theory that the universe underwent an extremely rapid expansion in its earliest moments, growing exponentially in a fraction of a second. Its significance lies in how it reshaped modern cosmology by offering explanations for features of the universe that otherwise appear puzzling. Despite its success, the fundamental cause of inflation and the nature of the field driving it remain unresolved mysteries. The roots of inflation trace back to the late 20th century, when physicists confronted problems in the standard Big Bang model. Alan Guth first proposed inflation in 1980, building on earlier insights from particle physics and cosmology. Subsequent refinements by Andre Linde and others transformed inflation from a bold idea into a central framework for understanding the early universe. At its core, inflation relies on the behavior of a hypothetical scalar field, often called the inflaton, whose energy caused space itself to expand. This mechanism explains why the universe appears geometrically flat, uniform in temperature, and largely isotropic. Quantum fluctuations during inflation were stretched to cosmic scales, seeding the formation of galaxies and large-scale structure. Several models of inflation exist, ranging from simple single-field scenarios to complex multi-field and eternal inflation frameworks. These models differ in mathematical form and physical interpretation, yet aim to describe the same primordial process. Observational support comes primarily from measurements of the cosmic microwave background, especially its temperature fluctuations and polarization patterns. While broadly consistent with inflation, certain anomalies persist and invite caution. Challenges include identifying the inflaton, reconciling inflation with quantum gravity, and addressing the possibility of multiple universes. Inflation connects deeply to particle physics, dark energy, and the origin of cosmic structure. Future observations and theoretical advances may transform inflation from a compelling hypothesis into a deeper understanding of cosmic beginnings. Flatness of the universe. The flatness of the universe refers to the large-scale geometric property of space, describing whether cosmic geometry is open, closed, or flat. Its significance lies at the heart of cosmology as it determines the universe's fate, expansion, and underlying physical laws. A central mystery is why the universe appears so close to perfectly flat despite conditions that should have driven it away from this state. Early ideas about cosmic geometry trace back to Euclidean geometry and were transformed by Einstein's general theory of relativity, which linked matter and energy to the curvature of spacetime. Scientists such as Alexander Friedmann and Georges Lemaitre developed dynamic models of the universe, while later observations refined these ideas. Over time, flatness emerged as a surprising and persistent feature. In cosmology, flatness means that parallel lines never meet and the angles of a triangle sum to 180 degrees. It is quantified by the density parameter, which compares the actual density of the universe to a critical value. Small deviations from this balance would grow dramatically over time, making the observed near flatness remarkable. Modern theories invoke cosmic inflation, a brief period of rapid expansion that smoothed out curvature. Alternative models explore modified gravity or cyclic universes, using both mathematical formalisms and conceptual frameworks. Observational evidence comes from measurements of the cosmic microwave background, galaxy distributions, and gravitational lensing. These data strongly support flat geometry, though minor anomalies persist. Challenges remain, including explaining the initial conditions that enabled inflation and resolving tensions between measurements. Flatness connects to dark energy, quantum gravity, and the origin of the universe itself. Future missions and theoretical advances may clarify these puzzles, offering deeper insight into why the universe is balanced on the edge of flatness and what that reveals about reality itself. Multiverse. The concept of the multiverse suggests that our universe may be one among countless others, each with its own distinct laws, constants, and realities. In physics and cosmology, this notion challenges our understanding of existence itself, questioning whether the cosmos we observe is the entirety of reality or merely a fragment of a far vaster landscape. The profound significance lies in its potential to explain fundamental fine-tuning and the apparent improbability of life-permitting conditions. Yet, the multiverse remains an enigma, largely inaccessible to direct observation, making it one of the most tantalizing open questions in modern science. Early speculations trace back to ancient philosophical ideas of infinite worlds, but scientific formulations emerged with inflationary cosmology in the late 20th century. Key figures such as Alan Guth, Andre Linde, and Max Tegmark advanced theoretical frameworks that formalized these ideas, evolving from abstract speculation to mathematically grounded models. Over time, the multiverse concept transitioned from philosophical curiosity to a legitimate scientific inquiry. At the heart of multiverse theories are principles of quantum mechanics, cosmic inflation, and string theory. Concepts such as bubble universes, parallel timelines, and higher dimensional spaces provide mechanisms for how multiple universes might arise. Phenomena like quantum superposition and vacuum fluctuations illustrate potential pathways for universe creation and divergence. Theoretical models include the level IV multiverse classification, eternal inflation, and the string landscape, each proposing distinct structures and origins. Observational evidence remains indirect, relying on cosmic microwave background anomalies, gravitational waves, or fine-tuning arguments. Persistent challenges involve testability, falsifiability, and reconciling paradoxes, like Boltzmann brains or the measure problem. Connections extend to dark energy, the anthropic principle, and the ultimate fate of the cosmos. Future prospects involve precision cosmology, high-energy physics experiments, and advancements in quantum gravity, offering possibilities for new insights or revolutionary breakthroughs. The multiverse embodies both the limits of human comprehension and the enduring drive to explore the unknown, inspiring curiosity and philosophical reflection on the nature of reality. Fate of the universe. The ultimate destiny of the universe has captivated scientists and philosophers alike, representing a central question in cosmology. Understanding this fate illuminates the fundamental laws governing space, time, and matter, while probing the limits of physics itself. Despite remarkable advances, the universe's long-term trajectory remains uncertain, posing profound scientific and philosophical challenges. Historically, early contemplations of cosmic destiny emerged from philosophical and theological perspectives. With the advent of Newtonian mechanics and later, Einstein's general relativity cosmology transformed into a rigorous scientific discipline. Key figures such as Edwin Hubble, whose observations of galactic redshifts revealed cosmic expansion, and Albert Einstein, whose equations predicted diverse cosmic evolutions, shaped our understanding over the 20th century. Central to this inquiry are concepts such as cosmic expansion, dark energy, and entropy. The dynamics of space-time, governed by general relativity, dictate the expansion rate and curvature of the universe. Phenomena like cosmic microwave background radiation and the large-scale structure of matter serve as empirical windows into these processes, linking theory with observation. Current theoretical frameworks explore scenarios including the Big Freeze, Big Crunch, and Big Rip, each grounded in the interplay between gravity, expansion, and dark energy. Competing models employ both analytical solutions to Einstein's equations and numerical simulations to predict long-term outcomes. Observational evidence from Type Ia supernovae, galaxy surveys, and CMB anisotropies supports an accelerating expansion driven by dark energy, though discrepancies in Hubble constant measurements hint at unresolved complexities. These challenges highlight limitations in our comprehension of fundamental physics. The fate of the universe connects to dark matter, quantum gravity, and the arrow of time, offering profound implications for our understanding of reality. Future missions, advanced telescopes, and theoretical breakthroughs may refine these predictions, gradually transforming speculation into empirical certainty. The question remains open, inspiring deep inquiry and reflection on the cosmos' ultimate destiny. Galaxy rotation problem. The motion of galaxies has long intrigued physicists and cosmologists, revealing deep insights into the structure of the universe. Understanding galaxy rotation is essential not only for mapping cosmic dynamics, but also for probing the elusive nature of dark matter. Observations show stars in galaxies orbit at speeds that defy predictions based on visible matter alone, presenting one of modern astrophysics' most profound mysteries. Early astronomical observations by Fritz Zwicky and Vera Rubin laid the groundwork for this enigma. Zwicky's study of galaxy clusters in the 1930s suggested the presence of unseen mass, while Rubin's precise measurements of stellar velocities in the 1970s confirmed that stars in the outskirts of galaxies rotated unexpectedly fast. These discoveries challenged classical Newtonian mechanics and reshaped our understanding of galactic structure. Galaxy rotation curves plot orbital velocity against radial distance from the center. Newtonian gravity predicts a decrease in velocity with distance, yet observed curves remain flat, implying additional unseen mass. This discrepancy underpins concepts like dark matter halos, which are theorized to envelop galaxies, influencing their rotational dynamics. Related phenomena include gravitational lensing, which independently supports the presence of invisible mass. Current models explore both dark matter and alternative gravity theories, such as modified Newtonian dynamics, MOND. Theoretical frameworks employ complex simulations to reconcile observed rotation curves with galactic mass distribution. Observational evidence from spectroscopic surveys and radio measurements consistently supports anomalous rotation speeds, though some inconsistencies remain, especially in low-surface brightness galaxies. Challenges persist in identifying the exact nature of dark matter explaining velocity anomalies and integrating these findings into a unified cosmological model. These investigations connect to broader topics, such as galaxy formation, cosmic structure evolution, and the search for fundamental particles. Future prospects include high-resolution surveys, advanced simulations, and potential detection of dark matter candidates. Understanding galaxy rotation could unlock profound insights into the universe's composition, dynamics, and the fundamental laws governing cosmic motion, inspiring ongoing exploration and theoretical innovation. Fast radio bursts. Fast radio bursts, or FRBs, are intense, millisecond-long flashes of radio waves originating from distant galaxies, captivating astronomers with their sudden enigmatic appearance. These bursts carry enormous energy, sometimes releasing in a millisecond as much as the sun emits in a day, offering a unique probe into the extreme conditions of the universe. Their significance lies in their potential to illuminate the intergalactic medium, test the laws of physics under extreme environments, and perhaps reveal new astrophysical phenomena yet to be understood. The first recorded FRB in 2007 challenged conventional astrophysical models, prompting a surge of observational and theoretical efforts. Pioneering radio surveys and instruments, such as the Parkes Observatory and later CHIME, identified additional events, expanding the known catalog and revealing patterns that hinted at both repeating and non-repeating sources. These discoveries transformed FRBs from curiosities into a recognized class of cosmic phenomena. FRBs are characterized by dispersion measures, polarization, and frequency structure, suggesting propagation through ionized media and possible interactions with magnetic fields. The underlying physics may involve neutron stars, magnetars, or exotic mechanisms, such as cosmic string interactions. Their brevity and intensity connect them to phenomena like pulsar emissions and gamma-ray bursts, although the exact mechanism remains elusive. Current theories range from magnetar starquakes and plasma lensing to binary neutron star mergers, each supported by mathematical modeling and computer simulations, but none conclusively explaining all observed properties. Observational data, including precise localization and multi-wavelength follow-ups, support some models, while revealing anomalies such as ultra-high repetition rates and unexpected polarization changes. Challenges persist in reconciling bursts' energy scales, repeatability, and origin environments. Their study intersects with dark matter research, cosmic magnetic field mapping, and tests of general relativity. Future observatories and deep surveys promise refined measurements, potentially unlocking the origin and mechanics of FRBs, advancing cosmology and high-energy astrophysics. Ultimately, FRBs exemplify the universe's persistent mysteries, inspiring inquiry into phenomena at the frontier of human understanding, where each detection may redefine our grasp of cosmic extremes. Gamma-ray bursts. Gamma-ray bursts, or GRBs, are the universe's most energetic explosions, emitting in seconds more energy than the sun will radiate over its entire lifetime. These fleeting yet intense phenomena are pivotal in cosmology, offering insights into stellar death, black hole formation, and the extreme physics governing high-energy astrophysics. Despite decades of study, the precise mechanisms driving GRBs and their progenitors remain partially enigmatic, challenging our understanding of relativistic jets and cosmic evolution. Initial detection of GRBs in the late 1960s by Vela satellites, originally monitoring nuclear tests, surprised the scientific community. Early interpretations varied widely from solar flares to distant supernovae until systematic observations identified extragalactic origins. Pioneering contributions by scientists such as Bohdan Paczynski and Gerald Fishman helped frame the modern understanding, evolving from simple burst catalogs to detailed light curve analyses and afterglow studies. At their core, GRBs involve the rapid release of gamma photons via highly relativistic jets. Long-duration bursts are typically linked to massive star collapses, forming black holes, while short bursts often originate from compact binary mergers, such as neutron-star collisions. These events also produce synchrotron radiation, gravitational waves, and neutrino emissions, connecting GRBs to a suite of high-energy astrophysical phenomena. Theoretical frameworks range from the collapsor model to magnetar-driven bursts with competing hypotheses, exploring jet composition, energy dissipation mechanisms, and emission geometry. Observational evidence from satellites like Swift and Fermi provides detailed spectral, temporal, and positional data, though anomalies like ultra-long GRBs and unusual afterglow behaviors persist. Current challenges include modeling the extreme relativistic physics, reconciling observed diversity, and understanding progenitor environments. GRBs intersect with broader questions in cosmology, such as star formation rates, the intergalactic medium, and dark energy effects. Future missions promise higher-resolution gamma-ray detection, multi-messenger observations, and refined theoretical models. Unraveling GRBs may not only elucidate stellar death and black hole physics, but also deepen our grasp of the universe's most violent processes, inspiring continued exploration of the cosmos. Primordial black holes. Primordial black holes are hypothetical remnants from the earliest moments of the universe, formed not from stellar collapse, but from extreme density fluctuations during the first fractions of a second after the Big Bang. Their existence carries profound significance, offering a potential window into the conditions of the infant cosmos and a candidate explanation for dark matter, one of the most persistent mysteries in modern cosmology. The concept traces back to the 1970s with Stephen Hawking and Yakov Zeldovich proposing that sufficiently dense regions in the primordial universe could collapse under their own gravity to form black holes. Initial ideas were largely theoretical, but they spurred decades of inquiry into the intersection of general relativity, quantum mechanics, and cosmology. Over time, refinements in inflationary theory and high-energy physics have shaped evolving models of their formation and potential mass distribution. Primordial black holes are defined by their extreme compactness and formation epoch differing fundamentally from stellar black holes. They interact gravitationally with surrounding matter and can theoretically emit Hawking radiation leading to gradual evaporation. These mechanisms link them to phenomena such as gamma-ray bursts and gravitational lensing effects, which could betray their presence despite their elusive nature. Contemporary models vary widely. Some posit primordial black holes as dark matter constituents, while others suggest a negligible cosmic abundance. Mathematical frameworks employ relativistic perturbation theory and inflationary dynamics to estimate formation probabilities and mass spectra, highlighting competing hypotheses about their origin and evolution. Observationally, searches focus on microlensing surveys, cosmic microwave background anomalies, and gravitational wave signals. While some candidate detections exist, data remain inconclusive and constraints on their abundance and mass remain stringent. Challenges persist, particularly in distinguishing their signals from other astrophysical phenomena and resolving tensions between theory and observation. Connections to broader physics are profound, touching on quantum gravity, early universe cosmology, and dark matter research. Future prospects include next-generation gravitational wave detectors and refined CMB analysis, which could either confirm their existence or further constrain their role. Understanding primordial black holes would illuminate the universe's first instance, offering insights that bridge the infinitesimal and the cosmic. Their study remains a frontier of inquiry, blending rigorous science with philosophical reflection on the origins of reality. Dark flow. The cosmos, vast and intricate, hides motions that defy conventional explanations. One such enigma is dark flow, a large-scale, peculiar motion of galaxy clusters, seemingly directed toward a specific region beyond the observable universe. Its significance lies in challenging our understanding of gravitational influences and cosmic homogeneity, posing profound questions about structures beyond the cosmic horizon and the fundamental nature of the universe. Early evidence emerged from precise measurements of the cosmic microwave background, where subtle deviations in the thermal imprint hinted at anomalous motions. Key contributions came from studies using the Wilkinson microwave anisotropy probe, revealing coherent cluster velocities, inconsistent with predictions from standard cosmology. Over time, the phenomenon has prompted debates and refinements in observational techniques, yet its origin remains elusive. Dark flow involves gravitationally induced peculiar velocities, defined as deviations from the universal expansion described by Hubble's law. These motions may be influenced by massive structures, voids, or even domains outside the observable universe. Related phenomena include bulk flows and cosmic anisotropies, which similarly probe the large-scale structure of space-time. Current theoretical models attempt to reconcile these observations. Some propose vast superclusters or anisotropic distributions beyond detection limits, while others invoke exotic physics or modifications of gravitational theory. Mathematical treatments involve velocity fields and statistical analyses of cluster motions across gigaparsec scales. Observational evidence relies on galaxy cluster surveys, X-ray measurements, and CMB anisotropies. While coherent motions are detected, results vary and some data show inconsistencies with simulations based on CDM cosmology. Challenges include the limits of current instrumentation, potential systematic biases, and the profound implications of motion originating beyond the observable universe. Open questions drive research into cosmic topology, dark energy dynamics, and uncharted gravitational influences. Dark flow connects to fundamental cosmology, dark matter distribution, and the universe's ultimate fate. If understood, it may reshape our comprehension of cosmic structure and unseen forces. Future missions with higher precision combined with refined theoretical models promise breakthroughs potentially revealing the unseen scaffolding of the cosmos. Dark flow remains a profound mystery, inspiring both scientific inquiry and philosophical reflection on the universe's hidden depths. Cosmic microwave background anomalies. The cosmic microwave background, or CMB, is the residual radiation from the Big Bang permeating the universe and offering a snapshot of its infancy. As a cornerstone of modern cosmology, it provides critical insight into the universe's origin, composition, and evolution. Yet subtle irregularities in its temperature distribution pose enduring puzzles, challenging the completeness of the standard cosmological model. The discovery of the CMB in 1965 by Arno Penzias and Robert Wilson confirmed theoretical predictions by George Gamow and colleagues. Subsequent missions, including COBE, WMAP, and Planck, refined measurements of its uniformity revealing minute fluctuations that encode the early universe's structure. Over decades, cosmologists have traced these anomalies, noting unexpected alignments and temperature asymmetries, often termed the CMB anomalies. At the heart of these observations are principles of blackbody radiation, photon decoupling, and quantum fluctuations during inflation. The anisotropies in the CMB, representing density variations, seeded large-scale cosmic structures. Phenomena such as the Sachs-Wolf effect and integrated Sachs-Wolf effect describe how gravitational potentials imprint on these primordial photons, linking microphysics with cosmic-scale observations. Theoretical models attempt to explain these anomalies through variations in inflationary scenarios, topological features of the universe, or unrecognized cosmic foregrounds. Competing frameworks invoke statistical deviations, multiverse interactions, or new physics beyond CDM. Mathematical approaches rely on spherical harmonics decomposition, power spectrum analysis, and correlation studies to quantify deviations. Empirical evidence, primarily from Planck, highlights temperature multipole alignments, the low quadrupole, and the cold spot features, inconsistent with purely random Gaussian fluctuations. These irregularities underscore limitations in predictive power and fuel debates on their cosmological significance. Understanding CMB anomalies connects to dark energy, cosmic topology, and early universe physics. Upcoming missions and refined simulations aim to unravel these mysteries, potentially revolutionizing comprehension of cosmic origins and fundamental laws. The pursuit remains a testament to humanity's drive to decode the universe, where each anomaly challenges us to rethink the known and explore the profound unknown. Variable physical constants. The universe is governed by a set of fundamental constants numbers, like the speed of light, Planck's constant, and the gravitational constant that define the very fabric of reality. These constants appear immutable, yet the possibility that they might vary over space or time challenges our deepest understanding of physics and cosmology. Exploring variable physical constants is crucial, as even minute changes could reshape the evolution of the cosmos, alter atomic structures, and redefine the laws of nature, posing profound questions about the stability and origin of physical law itself. Historically, constants were treated as fixed by definition. Early 20th century experiments, from Michelson-Morley's measurement of light speed to Planck's quantization of energy, reinforced their constancy. Key figures such as Dirac speculated that constants might evolve cosmically, linking them to the universe's age and structure. Over decades, theoretical frameworks have expanded, allowing for the conceptual flexibility of constants without violating observational constraints. Central to this topic are dimensionless quantities, like the fine structure constant, which governs electromagnetic interactions, and the gravitational coupling constant. Variations could manifest in atomic spectra, molecular bonds, or cosmological expansion, connecting microscopic physics to astronomical observations. Mechanisms for change may involve scalar fields, higher dimensional effects, or unknown forces. Current theories explore both static and dynamic scenarios. String theory, varying speed of light models, and quintessence cosmologies offer competing approaches, often framed mathematically through differential evolution equations or coupling constants dependent on scalar fields. Empirical evidence remains subtle. Spectroscopic data from distant quasars hint at possible small deviations in the fine structure constant, while atomic clocks constrain local temporal changes with extraordinary precision. Conflicting results underscore the challenge of detection and interpretation. Open questions abound. Are constants truly variable, or are anomalies observational artifacts? Could variations reconcile cosmological tensions such as the Hubble discrepancy? Understanding these possibilities could unify particle physics, cosmology, and quantum gravity. Connections extend to dark energy, inflation, and multiverse hypotheses. Future probes, next-generation telescopes, precision metrology, and advanced simulations promise to test these ideas rigorously. Resolving the variability of constants may redefine the concept of physical law itself. The quest to understand variable physical constants blends philosophy, mathematics, and observation, inviting us to question the very invariance of nature and to explore the universe not as static, but as a dynamic, evolving tapestry of possibility. Wavefunction collapse. The wavefunction collapse represents one of the most profound puzzles in quantum mechanics, describing how a quantum system transitions from a superposition of multiple possible states into a single definite outcome. Its significance extends beyond physics, touching the foundations of reality, measurement, and even cosmology, where the behavior of quantum systems underpins the formation of the universe's large-scale structure. Yet, despite decades of study, the precise mechanism behind this collapse remains enigmatic, posing a fundamental question. How and why does potentiality resolve into actuality? Early quantum theory, pioneered by Max Planck and Niels Bohr, laid the groundwork for understanding quantum states, while Erwin Schrödinger formalized the wave function, introducing superposition as a central principle. Key experiments, including the double-slit experiment and the Stern-Gerlach experiment, highlighted the non-classical behavior of particles, revealing the necessity of a collapse postulate to reconcile observation with theory. Over time, interpretations evolved from the Copenhagen view to more recent approaches like decoherence theory and objective collapse models. The wave function itself encodes all probabilistic information about a system governed by the Schrödinger equation. Collapse occurs when measurement or interaction forces the system into a specific eigenstate, a phenomenon intertwined with entanglement, decoherence, and quantum non-locality. Theoretical frameworks range from standard Copenhagen interpretation to many worlds and GRW spontaneous collapse, each offering conceptual and mathematical strategies to explain or circumvent collapse. Experimental evidence includes photon polarization measurements, quantum tomography, and interference pattern observations, all consistent with probabilistic outcomes, yet occasionally exhibiting anomalies that challenge deterministic predictions. Persistent questions include the role of consciousness, the boundary between classical and quantum worlds, and the emergence of objective reality. Wavefunction collapse connects deeply to broader physics, influencing quantum computing, cosmology, and fundamental questions about reality. Future explorations through advanced interferometry, entangled particle studies, and refined theoretical models may illuminate this elusive process, offering insights into the very nature of existence. Understanding it promises not only practical applications, but also profound philosophical revelations about the fabric of reality. Quantum randomness. Quantum randomness represents one of the most profound and enigmatic aspects of modern physics. At the heart of quantum mechanics lies the principle that certain events at the microscopic scale occur without deterministic predictability, a stark contrast to classical physics. This intrinsic unpredictability challenges our intuitive understanding of causality and plays a pivotal role in fields ranging from particle physics to cosmology, influencing theories about the fundamental nature of reality and the origin of the universe. Historically, the concept emerged from early 20th century experiments on atomic and subatomic particles. Key figures such as Max Planck, Niels Bohr, and Werner Heisenberg developed the foundations of quantum theory, culminating in Heisenberg's uncertainty principle, which formalized the inherent limits on predicting outcomes simultaneously. Over time, interpretations evolved from the Copenhagen interpretation, emphasizing probabilistic outcomes, to alternative frameworks exploring hidden variables. Core principles include superposition, wavefunction collapse, and quantum entanglement. Superposition allows particles to exist in multiple states until measured, while wavefunction collapse reflects the transition from potentiality to reality. Related phenomena, such as spontaneous emission and quantum tunneling, exemplify randomness manifesting in measurable events, reinforcing its non-deterministic character. Current models rely on quantum mechanics as the primary framework, with competing hypotheses exploring deterministic hidden variable theories like Bohmian mechanics. Mathematical approaches employ probability amplitudes, density matrices, and stochastic processes to quantify uncertainty. Empirical evidence arises from experiments like photon polarization, electron diffraction, and Bell test experiments, consistently confirming probabilistic predictions. Yet anomalies, such as unexplained correlations in entangled systems, continue to intrigue researchers. Challenges include reconciling randomness with relativity, understanding its role in cosmological evolution, and integrating it into quantum gravity. Its connections to information theory, chaos, and the arrow of time suggest profound implications, if fully understood. Future prospects involve more precise quantum control, advanced Bell tests, and applications in quantum computing and cryptography. Resolving these mysteries could redefine our comprehension of determinism, causality, and the universe itself, inspiring continued exploration into the unpredictable quantum realm. Observer-dependent reality. The nature of reality may not exist independently of the observer, challenging classical notions of an objective universe. This concept is pivotal in quantum mechanics and cosmology, suggesting that observation itself can shape the state of physical systems. Its significance lies in questioning the foundational assumptions about reality, measurement, and the limits of human knowledge, raising profound philosophical and scientific inquiries. Historically, early quantum experiments, such as the double-slit experiment, hinted at observer influence on outcomes. Pioneering scientists like Niels Bohr and Werner Heisenberg formulated principles emphasizing the role of measurement, while Schrödinger's thought experiments further illustrated observer-dependent phenomena. Over decades, understanding has evolved from abstract philosophical speculation to experimentally testable predictions. Core concepts involve wavefunction collapse, superposition, and the uncertainty principle. These principles describe how particles exist in multiple states simultaneously until measured, and how the act of observation restricts knowledge of complementary properties. Related phenomena include quantum entanglement and decoherence, demonstrating how correlations and environmental interactions influence perceived reality. Contemporary theories explore frameworks such as the Copenhagen interpretation, many worlds, and relational quantum mechanics. Competing hypotheses debate whether reality is fundamentally probabilistic, deterministic, across branching universes, or relationally constructed between systems. Mathematical formalisms quantify probabilities, correlations, and measurement outcomes. Empirical evidence arises from quantum interference experiments, delayed choice setups, and tests of entanglement, consistently confirming that measurement alters system behavior. However, anomalies persist in reconciling quantum mechanics with gravity and cosmological observations. Challenges include resolving paradoxes like Wigner's friend and integrating observer effects into a universal theory. Open research areas probe consciousness, decoherence limits, and quantum gravity implications. Connections extend to the nature of time, information theory, and the universe's initial conditions, implying that resolving observer-dependent reality could reshape our understanding of existence itself. Future prospects involve high-precision quantum experiments, advanced cosmological surveys, and theoretical progress in quantum gravity and information physics, potentially unveiling a deeper, unified description of reality. Observer-dependent reality underscores the profound interplay between observation and existence, leaving mysteries that continue to challenge and inspire scientific and philosophical exploration. Quantum entanglement. Quantum entanglement is a profound phenomenon in quantum mechanics, where two or more particles become interconnected, such that the state of one instantaneously influences the state of the other, regardless of spatial separation. This concept challenges classical intuitions about locality and causality, positioning it as a cornerstone of modern physics and a tantalizing puzzle in cosmology. Despite rigorous experimental verification, the underlying mechanism of this instantaneous connection remains one of the most compelling mysteries in science. The notion of entanglement emerged from early quantum theory debates, notably in the 1935 Einstein-Podolsky-Rosen paradox, which questioned whether quantum mechanics offered a complete description of reality. Subsequent experiments, including those by John Bell, provided testable inequalities, culminating in Elaine Aspect's landmark experiments in the 1980s, which offered strong evidence for entanglement, transforming it from philosophical speculation to empirical reality. At its core, entanglement involves superposition, quantum states, and non-local correlations. When entangled particles share a combined wavefunction, measurement of one immediately constrains the possible outcomes of the other. Related phenomena include quantum teleportation and decoherence, both pivotal in quantum information science and technology. Contemporary theories interpret entanglement within frameworks such as quantum field theory and the formalism of density matrices, while alternative models explore hidden variables or retrocausal explanations. The mathematics often employs tensor products and Hilbert space representations to describe correlations rigorously. Experimental evidence spans photonic, atomic, and solid-state systems, consistently confirming entanglement. Yet anomalies like entanglement sudden death and challenges in scaling quantum networks remain unresolved. Entanglement connects deeply with quantum computing, black hole information paradoxes, and the fundamental nature of spacetime, suggesting revolutionary implications if fully understood. Future prospects include larger-scale entangled systems, enhanced quantum communication and potential insights into the fabric of reality itself. Ultimately, quantum entanglement exemplifies the tension between experimental certainty and conceptual mystery, inviting ongoing exploration and philosophical reflection on the limits of knowledge and the interconnectedness of the universe. Quantum gravity. Quantum gravity represents one of the most profound frontiers in modern physics, striving to reconcile the principles of quantum mechanics with the geometric framework of general relativity. Its significance lies in bridging the gap between the microscopic world of particles and the macroscopic fabric of spacetime, offering insights into black holes, the Big Bang, and the fundamental structure of the universe. Despite decades of research, a complete and consistent theory remains elusive, leaving questions about the quantum nature of gravity unanswered. The quest for quantum gravity traces back to early 20th century breakthroughs. Einstein's general relativity reshaped our understanding of spacetime, while the emergence of quantum mechanics revealed the probabilistic behavior of matter and energy. Key figures including Niels Bohr, Werner Heisenberg, and Richard Feynman laid foundational principles, and early attempts to quantize gravity highlighted conceptual challenges that persist today. Over time, approaches evolved from perturbative techniques to more sophisticated frameworks, reflecting the interplay of theoretical innovation and experimental constraint. Central to quantum gravity are concepts such as spacetime quantization, graviton exchange, and Planck scale phenomena. The theory seeks to describe how gravity operates at quantum scales, potentially manifesting in phenomena like black hole evaporation and cosmic singularities. Related effects, including Hawking radiation and the holographic principle, illustrate the deep entanglement of gravity and quantum information. Current models encompass string theory, loop quantum gravity, and causal dynamical triangulations, each proposing distinct mechanisms and mathematical formulations. While some predict extra dimensions or discrete spacetime, others emphasize spin networks or topological invariance. Observational evidence remains indirect, with gravitational wave detections, cosmic microwave background measurements, and high-energy astrophysical observations, offering constraints, yet leaving gaps and anomalies. Challenges include unifying these frameworks, resolving paradoxes like information loss, and making testable predictions. Quantum gravity intersects with cosmology, particle physics, and black hole thermodynamics, hinting at transformative implications for our understanding of reality. Future prospects involve next-generation observatories, refined theoretical models, and potential experimental probes of Planck-scale physics. Advancing this frontier promises not only to illuminate the nature of spacetime, but to inspire a deeper philosophical and scientific contemplation of the universe itself. Hidden variables. Hidden variables in physics refer to theoretical elements that could determine the behavior of quantum systems, with certainty challenging the inherent randomness of quantum mechanics. Their significance lies in the potential to reconcile classical determinism with quantum unpredictability, a question that touches the foundations of reality and cosmology. The central mystery persists. Is quantum indeterminacy fundamental, or is it a reflection of variables yet unseen? The concept emerged in the early 20th century as physicists grappled with quantum mechanics' probabilistic predictions. Pioneers like Einstein, Podolsky, and Rosen proposed that quantum theory might be incomplete, suggesting hidden variables could restore determinism. Later, David Bohm developed a deterministic interpretation, while John Bell formulated inequalities to test the viability of hidden variable theories, experimentally shaping the field's evolution. Hidden variables posit underlying parameters, influencing quantum states, potentially explaining phenomena like entanglement and superposition deterministically. Bohmian mechanics, for example, introduces a pilot wave, guiding particles, illustrating how hidden variables could function without contradicting observed quantum outcomes. These principles attempt to reconcile locality, realism, and causality with quantum observations. Current theories include deterministic frameworks like Bohmian mechanics and stochastic approaches, proposing probabilistic hidden influences. Competing hypotheses explore whether non-locality or contextuality is necessary, often analyzed through rigorous mathematical formalisms and conceptual models. Empirical investigations involve tests of Bell inequalities and experiments in entangled particle systems. While most results align with standard quantum mechanics, subtle anomalies occasionally provoke debate, leaving room for interpretation. Challenges include reconciling hidden variable theories with relativistic constraints, explaining quantum randomness, and addressing paradoxes like Schrödinger's cat. Active research explores foundational questions and novel experimental setups. The topic intersects with quantum information, cosmology, and the philosophy of science, linking to broader questions of determinism and reality. Resolving it could redefine our understanding of the universe's fundamental laws. Future prospects hinge on precision quantum experiments, advancements in quantum computing, and theoretical refinement, offering potential breakthroughs in the comprehension of reality. Hidden variables remain a profound enigma, urging continued exploration, philosophical reflection, and scientific inquiry into the deepest layers of the universe. Interpretation of quantum mechanics. Quantum mechanics, the foundation of modern physics, reveals a world that defies classical intuition. Its significance spans from explaining atomic behavior to shaping cosmology, yet its interpretation remains deeply enigmatic. Central to the mystery is the nature of reality itself. Does the wave function represent physical reality or merely knowledge of a system? The history of quantum theory began in the early 20th century with Planck's quantization of energy and Einstein's explanation of the photoelectric effect. Pioneering experiments by Bohr, Heisenberg, and Schrödinger established a framework where particles exhibit both wave and particle characteristics, evolving into a formalism rich in predictive power but philosophical ambiguity. Core concepts include the wave function, superposition, and entanglement, describing phenomena where particles exist in multiple states, simultaneously or instantaneously influence each other across distance. Principles such as Heisenberg's uncertainty principle reveal fundamental limits to what can be known, while quantum decoherence connects microscopic behavior to classical observation. Several theories aim to interpret quantum mechanics. The Copenhagen interpretation emphasizes measurement-induced collapse, while the many worlds interpretation proposes branching realities. Alternative approaches like de Broglie-Bohm theory and objective collapse models offer deterministic or stochastic perspectives. Mathematical formulations underpin each, yet no consensus resolves the interpretational divide. Empirical evidence supports quantum predictions through experiments like double-slit interference, Bell's inequality tests, and quantum computing demonstrations. Anomalies occasionally challenge models, highlighting subtleties in entanglement and non-locality. Challenges persist, including reconciling quantum mechanics with gravity, resolving the measurement problem, and understanding wave-function ontology. Active research explores quantum foundations, advanced simulations, and high-precision tests. Connections extend to cosmology, black hole physics, and information theory, with implications for the fabric of reality. Future prospects include novel quantum experiments, improved theoretical frameworks, and potential insights into the unification of physics. Quantum mechanics continues to inspire profound philosophical and scientific inquiry, revealing a universe simultaneously tangible and mysterious, compelling deeper exploration into the nature of existence. Arrow of time in quantum systems. The arrow of time in quantum systems represents a profound inquiry into why temporal progression appears unidirectional in a universe governed by fundamentally time-symmetric laws. Understanding this concept is pivotal not only in physics, but in cosmology, as it touches the foundations of entropy, causality, and the emergence of macroscopic order from microscopic reversibility. Despite decades of study, the reconciliation between quantum mechanics and the apparent irreversibility of time remains an open and tantalizing mystery. Historically, the notion of temporal asymmetry emerged from thermodynamics, notably through the second law, which posits entropy's inexorable increase. Pioneers such as Ludwig Boltzmann and Erwin Schrödinger grappled with statistical interpretations of time's flow, while modern quantum experiments probe decoherence and measurement-induced irreversibility. Over the decades, understanding has evolved from classical statistical analogies to rigorous quantum formulations, yet the fundamental question persists. Core concepts central to this discussion include entropy, quantum decoherence, and time-reversal symmetry. Decoherence explains how quantum superpositions collapse into classical outcomes, introducing an effective directionality. Related phenomena, such as the quantum Zeno effect and entanglement dynamics, further illustrate subtle mechanisms by which microscopic processes manifest temporal asymmetry. Current theories range from decoherence-based interpretations to approaches invoking cosmological boundary conditions. Competing hypotheses consider intrinsic quantum irreversibility versus emergent statistical effects, often explored through mathematical frameworks like density matrices and master equations. Evidence arises from controlled experiments on isolated quantum systems, demonstrating entropy growth and irreversible evolution, though anomalies and residual coherence challenge simple models. Major challenges include reconciling microscopic reversibility with macroscopic irreversibility, understanding the role of initial conditions, and quantifying the interplay of quantum correlations. Connections span black hole thermodynamics, cosmological expansion, and the measurement problem, suggesting profound implications if resolved. Future prospects hinge on advanced quantum simulations, ultra-cold atom experiments, and theoretical unification with gravity. Resolving these mysteries promises not only deeper comprehension of time itself, but also novel insights into the universe's fundamental architecture. Ultimately, the arrow of time in quantum systems exemplifies the intersection of physics and philosophy, highlighting both the elegance and enigma of temporal reality, inspiring continued exploration and intellectual curiosity. Macroscopic superposition. Imagine a world where objects, not just particles, can exist in multiple states simultaneously. Macroscopic superposition challenges our classical intuition, suggesting that quantum phenomena might extend beyond the microscopic realm. Its significance lies in bridging quantum mechanics and classical physics, potentially reshaping our understanding of reality itself. The central mystery remains: can macroscopic objects truly exhibit quantum superpositions, and if so, under what conditions? Early explorations into superposition stemmed from Schrödinger's famous thought experiment, illustrating the paradox of a cat both alive and dead. Pioneering experiments with electrons, photons, and superconducting circuits laid the foundation for extending quantum principles to larger scales. Over decades, theoretical and experimental approaches evolved, probing the boundary between quantum and classical domains. At the heart of macroscopic superposition are principles of quantum coherence, entanglement, and wavefunction collapse. Decoherence, the process by which interaction with the environment destroys superpositions, becomes increasingly significant as systems grow larger. Phenomena such as superconductivity, Bose-Einstein condensates, and optomechanical resonators illustrate these principles in controlled settings, offering glimpses of quantum behavior in macroscopic systems. Theoretical frameworks range from decoherence theory to objective collapse models and many worlds interpretations. Competing hypotheses attempt to explain whether superpositions persist at large scales or whether hidden mechanisms enforce classicality. Mathematical modeling often involves density matrices, Schrödinger equations, and master equations, accounting for environmental interactions. Experimental evidence is emerging from superconducting qubits, nanomechanical oscillators, and ultra-cold atomic ensembles. While some measurements confirm quantum coherence in relatively large systems, anomalies persist and true macroscopic superpositions remain elusive. Challenges include environmental isolation, measurement precision, and scaling effects. Macroscopic superposition connects deeply to quantum gravity, consciousness studies, and the measurement problem. If fully realized, it could revolutionize computation, communication, and our philosophical understanding of reality. Future prospects include space-based interferometry, improved cryogenic systems, and refined theoretical models, offering a pathway toward potentially observing superpositions in truly macroscopic objects. In essence, macroscopic superposition is both a profound scientific inquiry and a philosophical puzzle. Its exploration pushes the boundaries of physics, inspiring curiosity, debate, and the relentless pursuit of understanding the quantum nature of the universe. True randomness in quantum mechanics. Quantum mechanics challenges our classical intuition by introducing intrinsic unpredictability into the behavior of particles. Unlike deterministic systems, where future states can be precisely calculated, quantum systems exhibit outcomes that appear fundamentally random, such as the decay of a radioactive atom or the measurement of an electron's spin. Understanding this randomness is crucial not only for physics, but for cosmology, cryptography, and the foundations of reality, raising profound questions about the nature of causality and determinism. The journey toward this understanding began in the early 20th century, with Max Planck's quantization of energy and Albert Einstein's studies on the photoelectric effect. Niels Bohr, Werner Heisenberg, and Erwin Schrödinger contributed to formalizing quantum theory, introducing principles like superposition and uncertainty that implied inherent probabilistic behavior. Experiments such as the double-slit interference and Bell test experiments progressively reinforced the notion that quantum randomness is not merely epistemic, but potentially fundamental. Key concepts include wavefunction collapse, quantum superposition, and entanglement. The Born rule links wavefunction amplitudes to probabilities, while Heisenberg's uncertainty principle quantifies limits on simultaneously knowing certain pairs of properties. Phenomena, like quantum tunneling and decoherence, exemplify randomness, manifesting in observable effects. Current theories explore randomness through frameworks like the Copenhagen interpretation, many worlds interpretation, and objective collapse models. Competing hypotheses attempt to reconcile deterministic hidden variables with observed indeterminacy, though Bell inequalities constrain these possibilities. Experimental evidence, from photon polarization to electron spin measurements, consistently supports intrinsic randomness, yet anomalies and loopholes in tests continue to provoke debate. Open questions include reconciling quantum randomness with gravity, understanding the measurement problem, and exploring potential deterministic underpinnings. Quantum randomness connects deeply to cosmology, information theory, and the search for a unified physics framework. Upcoming experiments, such as advanced quantum computers and precision entanglement tests, may illuminate these mysteries. Ultimately, embracing quantum unpredictability reshapes our understanding of reality and invites continuous exploration into the fundamental nature of existence. Faster-than-light quantum effects. The concept of faster-than-light quantum effects challenges our fundamental understanding of space, time, and causality. These phenomena, most notably quantum entanglement, suggest that particles separated by vast distances can instantaneously influence each other, defying the classical speed limit set by light. Such effects are pivotal in quantum mechanics and cosmology, offering potential insights into the fabric of reality and the limits of information transfer. Yet they remain deeply mysterious and unresolved. Early explorations into quantum mechanics by pioneers such as Einstein, Podolsky, and Rosen highlighted the paradoxical nature of entanglement. Experiments by Elaine Aspect and others in the late 20th century provided empirical evidence supporting these counterintuitive predictions, gradually shaping our modern understanding of non-locality and quantum correlations. Over time, interpretations evolved from philosophical debates to rigorous experimental science. Key concepts include quantum superposition, entanglement, and non-locality. Quantum superposition allows particles to exist in multiple states simultaneously, while entanglement creates instantaneous correlations across distances. These effects challenge classical notions of causality, giving rise to phenomena like the violation of Bell inequalities, which test the limits of local realism. Current theoretical frameworks include standard quantum mechanics, quantum field theory, and interpretations such as many worlds and Bohmian mechanics. Competing hypotheses explore whether faster-than-light effects permit information transfer or merely correlations without causality violations. Mathematical approaches often rely on density matrices, Hilbert spaces, and relativistic constraints. Empirical evidence stems from precise photon and electron entanglement experiments showing correlations stronger than classical physics allows. Yet anomalies persist, particularly in understanding the transmission of information and potential hidden variables. The field faces challenges in reconciling quantum non-locality with relativity and in explaining entanglement in macroscopic systems. Research continues into quantum networks, teleportation, and cosmological implications. Connections span quantum computing, black hole information paradoxes, and fundamental cosmology. Future experiments in space-based entanglement and refined theoretical models may unlock unprecedented understanding of reality, potentially redefining our conception of space, time, and causality. the mystery endures, inviting both curiosity and philosophical reflection on the limits of human knowledge. Limits of quantum computation. Quantum computation promises to revolutionize our understanding of information processing, harnessing the principles of superposition and entanglement to perform tasks beyond classical capabilities. Its significance extends across physics and cosmology, offering potential insights into complex systems, black hole information paradoxes, and the fundamental limits of computation itself. Yet the precise boundaries of quantum computing remain a profound mystery, challenging both theorists and experimentalists. Early conceptual seeds were planted in the 1980s, with pioneers such as Richard Feynman and David Deutsch, who envisioned computing devices that exploit quantum mechanics. Deutsch formulated the first universal quantum computer model, while Peter Shor's groundbreaking algorithm for factoring large numbers demonstrated a concrete advantage over classical machines. Over the decades, these ideas have evolved into practical quantum circuits, error correction schemes, and scalable architectures. At the core, quantum computation relies on qubits, entanglement, superposition, and unitary evolution. Quantum gates manipulate states coherently, while phenomena like decoherence and quantum noise impose fundamental constraints. Related effects, such as the no-cloning theorem and quantum tunneling, illustrate the unique rules governing quantum information. Contemporary theories explore quantum complexity classes, fault-tolerant computation, and holographic principles, with competing hypotheses about the ultimate computational capacity of the universe. Mathematical models, like tensor networks and quantum circuit complexity, provide conceptual frameworks for these inquiries. Empirical efforts with superconducting qubits, trapped ions, and photonic systems yield evidence of small-scale quantum supremacy, yet experimental anomalies and noise-induced errors persist, highlighting unresolved questions. Current limitations include decoherence, error thresholds, and resource scaling, alongside paradoxes like the black hole information conundrum. Research actively probes quantum simulation, topological qubits, and hybrid architectures. Connections to broader physics emerge in quantum gravity, cosmological simulations, and information-theoretic interpretations of spacetime. Future prospects hinge on advanced qubit designs, improved coherence, and novel theoretical insights, promising breakthroughs that could redefine computation and physical law. Ultimately, understanding the limits of quantum computation remains a frontier of intellectual exploration, where every discovery deepens our grasp of reality and sparks new mysteries to unravel. Quantum decoherence. Quantum decoherence represents the gradual loss of quantum coherence in a system, marking the transition from the bizarre probabilistic realm of quantum mechanics to the deterministic world of classical physics. Its significance lies at the heart of understanding why macroscopic objects do not exhibit quantum superpositions, and it challenges our grasp of reality itself. Despite decades of study, the precise mechanisms and implications of decoherence remain an open question, entwined with the foundations of quantum theory and the measurement problem. Historically, the concept emerged as physicists grappled with the paradoxes of wavefunction collapse. Early experiments by scientists such as Schrödinger, with his famous cat thought experiment, and von Neumann's formalization of measurement, laid the groundwork. Over time, developments in quantum optics and mesoscopic systems have allowed experimental investigation, refining our comprehension of how environmental interactions suppress interference. At its core, decoherence arises when a quantum system interacts with its environment, entangling states and effectively leaking quantum information. Terms like density matrices, superposition, entanglement, and phase damping become essential. Phenomena such as the quantum Zeno effect and spin-bath interactions illustrate these mechanisms in practice. Theoretical frameworks include the density matrix formalism, master equations, and decoherent histories, while competing interpretations like many worlds versus objective collapse offer different conceptual lenses. Mathematical models quantify decoherence rates and environmental couplings, providing predictive power. Experimental evidence emerges from interference experiments, superconducting qubits and trapped ions, confirming theoretical predictions, yet revealing anomalies in complex or high-temperature systems. Challenges persist in fully reconciling decoherence with gravity, cosmology, and quantum-to-classical transitions, motivating ongoing research. Connections span quantum computing, cosmological inflation, and the nature of reality itself. Future prospects hinge on ultra-isolated quantum systems, advanced interferometry, and theoretical breakthroughs, potentially redefining the boundary between quantum and classical worlds. Quantum decoherence not only illuminates the fragility of quantum states, but also confronts us with profound questions about observation, reality, and the universe's fundamental structure. Breakdown of quantum mechanics. Quantum mechanics stands as one of the most profound pillars of modern physics, offering a framework to describe phenomena at atomic and subatomic scales. Its significance stretches beyond particle behavior, shaping our understanding of cosmology, black holes, and the early universe. Yet fundamental mysteries remain, such as the measurement problem and the nature of wavefunction collapse. The roots of quantum mechanics trace back to the early 20th century, beginning with Max Planck's quantization of energy and Einstein's explanation of the photoelectric effect. Pioneering experiments by Niels Bohr, Werner Heisenberg, and Erwin Schrödinger gradually unveiled discrete energy levels, uncertainty principles, and wave-particle duality, reshaping classical physics and laying the groundwork for quantum theory's evolution. At its core, quantum mechanics relies on principles such as superposition, entanglement, and probability amplitudes. Particles do not possess deterministic trajectories. Instead, their states are described by wavefunctions, evolving under the Schrödinger equation. Phenomena like tunneling, quantum interference, and non-local correlations exemplify these mechanisms, challenging intuitive notions of reality. Theoretical frameworks include canonical quantum mechanics, quantum field theory, and interpretations ranging from Copenhagen to many worlds. Competing hypotheses address foundational questions, employing mathematical formalism such as Hilbert spaces, operators, and path integrals, each offering distinct conceptual insights. Empirical support arises from spectroscopy, particle accelerators, and quantum optics experiments. Measurements of energy levels, Bell test violations, and superconducting qubits consistently affirm theoretical predictions, though anomalies, such as quantum gravity integration, remain unresolved. Current challenges encompass reconciling quantum mechanics with general relativity, understanding decoherence, and resolving paradoxes, like Schrödinger's cat. Research continues in quantum computing, entanglement experiments, and cosmological applications. Quantum mechanics intersects with fields like cosmology, condensed matter physics, and information theory, promising transformative insights. Future prospects include more precise tests of quantum foundations, advances in quantum technologies, and potential unification with gravity. Ultimately, quantum mechanics illuminates the fabric of reality, bridging theory and observation, while leaving profound questions open, inviting continuous inquiry and intellectual exploration. Unknown quantum particles. In the depths of the quantum realm, particles exist that defy conventional understanding, revealing the limits of modern physics. These unknown quantum particles, elusive and often theoretical, hold the key to phenomena that could reshape our grasp of matter, energy, and the universe itself. Their significance stretches from subatomic interactions to cosmological structures, offering potential insight into dark matter, quantum gravity, and the foundations of reality. Yet, despite decades of research, their properties remain largely mysterious, prompting profound questions about the very fabric of existence. The journey toward understanding began with early quantum theory, when Max Planck and Albert Einstein uncovered the quantization of energy. Subsequent experiments, including those by Wolfgang Pauli and Enrico Fermi, revealed particles, such as neutrinos, hinting at a hidden landscape of subatomic entities. Over time, theoretical frameworks expanded, evolving from the standard model to more speculative extensions, suggesting the presence of particles beyond current detection. Central to this exploration are concepts such as quantum superposition, wave-particle duality, and particle entanglement. These principles govern the behavior of known and unknown particles alike, producing phenomena like virtual particles and quantum tunneling, which challenge classical intuition. Theoretical models, including supersymmetry, string theory, and quantum field extensions, propose candidates for these mysterious entities, employing both mathematical formalism and conceptual innovation. Experimental efforts, from high-energy colliders to astrophysical observations, have provided indirect evidence, while anomalies in cosmic radiation and particle decay hint at phenomena yet unexplained. Limitations of existing models and paradoxes in quantum mechanics fuel ongoing research, linking unknown particles to broader questions of dark matter, vacuum energy, and multiverse hypotheses. Future prospects include next-generation detectors and theoretical refinements that may finally reveal these hidden components of reality. Unlocking their secrets could revolutionize physics, offering profound implications for our understanding of the cosmos, matter, and the ultimate nature of existence. Weakness of gravity. Gravity, the force governing the motion of planets, stars, and galaxies, is paradoxically the weakest of the fundamental interactions. Despite its universal influence, its subtlety challenges both theoretical understanding and experimental precision. This weakness not only shapes the large-scale structure of the cosmos, but also conceals deep mysteries about the nature of spacetime and matter, posing one of physics' most profound enigmas. Historically, gravity's comprehension began with Newton, who quantified its effects, yet treated it as an instantaneous action at a distance. Einstein revolutionized this view, with general relativity portraying gravity as the curvature of spacetime, yet even this elegant framework leaves unanswered why gravity is vastly weaker than the electromagnetic, strong, and weak nuclear forces. Experiments such as Cavendish's torsion balance laid the foundation for precise measurement, gradually refining the understanding of its strength. Gravity operates through mass-energy interactions, mediating motion via the geometry of spacetime, rather than through particle exchange in classical terms. Phenomena such as tidal forces, orbital mechanics, and gravitational lensing manifest its influence, yet its comparative feebleness allows galaxies to form while permitting subatomic interactions to dominate locally. Contemporary models attempt to explain this weakness. Hypotheses range from extra-dimensional leakage of gravitational influence in string theory to to modifications of gravity at cosmological scales. Mathematical frameworks, including quantum gravity and brane-world scenarios, seek to reconcile gravity's minute strength with quantum principles. Observational evidence, from planetary motions to gravitational waves, consistently confirms relativistic predictions, yet anomalies like dark matter and dark energy hint at missing aspects of the gravitational story. Precision experiments continue to probe submillimeter scales for deviations that might reveal hidden forces. The challenge remains: why does gravity occupy such a delicate niche in the hierarchy of forces? Resolving this could illuminate connections to particle physics, cosmology, and the fundamental architecture of reality. Upcoming experiments, theoretical advancements, and cosmological surveys promise potential breakthroughs, encouraging profound curiosity and relentless inquiry into this subtle yet universal force. Quantization of gravity. The quest to quantize gravity stands at the frontier of modern physics, seeking to unify the principles of general relativity with quantum mechanics. This endeavor is crucial as gravity governs the large-scale structure of the universe, while quantum phenomena dictate the behavior of the microscopic realm. Yet gravity resists the standard techniques of quantization, presenting one of the most profound mysteries in cosmology: how spacetime itself behaves at the Planck scale. Historically, gravity was described classically by Einstein's general relativity, while early quantum theorists like Planck and Heisenberg laid the foundations of quantum mechanics. Attempts to merge these frameworks began with linearized approximations and perturbative approaches, but fundamental inconsistencies emerged, prompting new conceptual approaches over decades. At its core, quantizing gravity requires defining the gravitational field in terms of discrete quantum excitations, often conceptualized as gravitons. Central principles include the interplay of spacetime curvature, energy momentum, and the uncertainty inherent in quantum states. Related phenomena, such as black hole thermodynamics and the Hawking radiation process, hint at quantum effects in strong gravitational fields. Contemporary models include string theory, which postulates vibrating fundamental strings, replacing point particles, and loop quantum gravity, which discretizes spacetime itself. Each framework offers competing mathematical approaches, from higher dimensional geometries to spin networks, aiming to resolve divergences and predict observable consequences. Observationally, gravitational wave detections, black hole imaging, and cosmological surveys provide indirect constraints, though no direct quantum gravity signatures have yet been measured. Some anomalies, like the information paradox, challenge conventional understanding. Major challenges remain: unifying the continuum of spacetime with quantum discreteness, resolving singularities, and experimentally probing Planck-scale phenomena. Connections span cosmology, particle physics, and fundamental metaphysics, offering potential insight into the origins of the universe. Future prospects involve precision cosmology, next-generation gravitational observatories, and refined theoretical tools, promising gradual illumination of this enigmatic domain. Understanding quantum gravity may redefine our conception of reality itself, bridging the infinitesimal and the cosmic in a coherent framework. Extraspatial dimensions. The concept of extraspatial dimensions extends our understanding of the universe beyond the familiar three-dimensional space, challenging conventional notions of reality. These additional dimensions, though imperceptible to everyday experience, could fundamentally alter our comprehension of gravity, particle physics, and cosmology, offering potential solutions to some of the deepest puzzles in science, such as the hierarchy problem and the nature of dark matter. The tantalizing question persists: could our universe be only a subset of a higher dimensional reality? Historically, the idea traces back to the early 20th century, when Theodore Kaluza and Oskar Klein proposed a unification of gravity and electromagnetism by introducing a fifth dimension. Over decades, string theory and M-theory have evolved this concept, suggesting that multiple compactified dimensions exist beyond perception, each influencing fundamental forces and particle behavior. These theories gained traction as physicists explored the mathematical elegance of higher dimensional spaces. Extraspatial dimensions are defined as dimensions beyond the observable three, often compactified at scales too small to detect directly. Their underlying mechanisms involve the behavior of fields and strings in higher dimensional manifolds, where phenomena like brane world scenarios suggest our universe might exist on a multidimensional membrane. Gravitational leakage into extra dimensions could explain why gravity is weaker than other forces, offering testable predictions. Current theoretical frameworks include string theory, M-theory, and large extra-dimension models, each proposing distinct geometrical and topological structures. Competing hypotheses explore warped versus flat extra dimensions with mathematical formulations describing how particles traverse or are confined within them. Observational evidence remains indirect. Experiments at the Large Hadron Collider and gravitational wave detectors seek signatures of Kaluza-Klein particles or deviations in Newtonian gravity. While no conclusive detections exist, anomalies continue to guide theoretical refinements. Challenges include the difficulty of direct detection, reconciling higher dimensional models with quantum field theory, and explaining cosmological observations. Connections extend to black hole physics, dark energy, and the multiverse hypothesis. Future prospects hinge on precision measurements, particle accelerator advances, and deeper mathematical insights, with the potential to transform our conception of reality. Understanding extra-spatial dimensions could redefine the boundaries of physics, cosmology, and human imagination. Origin of particle mass. The question of how particles acquire mass lies at the heart of modern physics, shaping our understanding of the universe from the subatomic scale to the cosmos itself. Mass is not merely a measure of an object's inertia. It is the gateway to the structure of matter, the formation of stars, and the evolution of galaxies. Despite its fundamental nature, the origin of particle mass remains a profound mystery, challenging both theoretical and experimental frameworks in physics. Historically, the concept of mass was intuitive, linked to weight and resistance to motion. Newtonian mechanics treated mass as intrinsic and immutable, yet the early 20th century brought a paradigm shift. Discoveries in quantum mechanics and relativity hinted that mass might emerge from interactions rather than exist as an inherent property. Theoretical contributions from scientists like Higgs, Englert, and Brout culminated in the proposal of a pervasive quantum field, capable of endowing particles with mass, a bold hypothesis, confirmed decades later through high-energy collider experiments. Central to understanding particle mass are concepts such as symmetry breaking, quantum fields, and the Higgs mechanism. Particles acquire mass through interactions with the Higgs field, a scalar field permeating the universe with the Higgs boson, acting as its observable manifestation. Related phenomena, including gauge boson masses and spontaneous symmetry breaking, illustrate how subtle field interactions shape the tangible properties of matter. Current theoretical models extend beyond the standard model, exploring alternatives like supersymmetry and technicolor, offering competing explanations for mass generation. Precision measurements from colliders, cosmic observations, and neutrino experiments provide supporting evidence, though anomalies in particle behavior hint at deeper layers yet unexplored. Challenges remain from understanding the mass hierarchy to integrating gravity. The quest intersects with dark matter, cosmological inflation, and unification theories, suggesting that unraveling particle mass could illuminate the most profound cosmic mysteries. Future experiments, including next-generation colliders and refined cosmological probes, promise to refine or revolutionize our understanding. The origin of particle mass is more than a scientific inquiry. It is an invitation to probe the fabric of reality itself. Origin of electric charge. Electric charge is one of the most fundamental properties of matter, underlying the structure of atoms and the forces that govern the universe. Its significance spans from classical electromagnetism to quantum field theory, shaping our understanding of particle interactions and cosmological evolution. Despite centuries of study, the origin of electric charge remains a profound mystery, raising questions about why particles possess specific, discrete values and how these charges arise at a fundamental level. Historically, the study of charge began with the observation of static electricity by the Greeks, but systematic investigation emerged in the 18th century with Benjamin Franklin's experiments. The identification of electrons by J.J. Thomson and subsequent studies of protons and neutrons provided the first quantitative insights into charged particles. Over time, the concept of charge evolved from a macroscopic curiosity to a cornerstone of particle physics, with discoveries of quarks, revealing fractional charges and deepening the enigma of charge quantization. Electric charge is defined as a conserved property that determines the electromagnetic interaction of particles. Positive and negative charges generate electric fields and interact via Coulomb's law, while the movement of charges produces magnetic fields. Phenomena such as polarization, induction, and the quantum Hall effect exemplify the pervasive influence of charge in both classical and quantum domains. Current theories, including the Standard Model of particle physics, describe charge as an intrinsic attribute of particles, yet the deeper origin why charge values are quantized and how they emerge is still debated. Grand unified theories and string theory offer frameworks, but definitive evidence remains elusive. Experimental observations from particle accelerators, atomic spectroscopy, and high-energy collisions support charge conservation and quantization, yet anomalies like the possible existence of millicharged particles challenge current models. Researchers continue to probe these frontiers, seeking answers that may link electric charge to symmetry breaking, topological structures, or the fabric of spacetime itself. Understanding the origin of charge could illuminate other fundamental mysteries, from the nature of dark matter to the forces shaping the early universe. Future experiments and theoretical advances promise to refine our grasp, yet the question persists, inspiring curiosity and driving the quest to decode one of physics' most profound enigmas. Magnetic monopoles. Magnetic monopoles are hypothetical particles that carry isolated magnetic charge, representing a single north or south magnetic pole. Unlike conventional magnets, which always exist as dipoles, monopoles would fundamentally alter our understanding of electromagnetic theory. Their existence could provide critical insights into charge quantization and unify disparate forces in the universe, presenting a tantalizing frontier in both physics and cosmology. Yet, despite decades of theoretical and experimental pursuit, magnetic monopoles remain elusive, embodying one of the profound mysteries of modern science. The idea of magnetic monopoles traces back to Pierre Curie in the late 19th century, who suggested isolated magnetic charges might exist. In the 20th century, Paul Dirac formalized the concept, mathematically demonstrating that monopoles would explain why electric charge is quantized. Subsequent efforts by researchers such as Blaise Cabrera, who reported a possible detection in 1982, have kept the search alive, shaping evolving theories and experimental strategies. At their core, magnetic monopoles challenge Maxwell's equations, requiring modifications to incorporate a source term for magnetic charge. They are predicted in grand unified theories, where symmetry breaking in the early universe could have produced monopoles. Related phenomena, such as the Dirac string and topological solitons, provide conceptual frameworks for understanding their properties and potential interactions. Current theoretical models range from classical field extensions to quantum and string-theoretic approaches. Some hypotheses suggest monopoles are exceedingly massive and rare, while others propose transient or confined states. Observational searches, including superconducting detectors and cosmic ray studies, have yielded tantalizing hints, but no conclusive evidence, leaving anomalies unresolved. If discovered, monopoles could redefine cosmology, illuminate the early universe, and link to other unsolved mysteries like dark matter. Ongoing experiments and theoretical refinements promise potential breakthroughs, ensuring that the pursuit of magnetic monopoles continues to inspire deep scientific curiosity and philosophical reflection about the fundamental nature of reality. Unknown fundamental forces. In the vast tapestry of the universe, forces govern the behavior of matter and energy, yet physics hints at influences beyond the known four: gravity, electromagnetism, and the strong and weak nuclear forces. The concept of unknown fundamental forces challenges our understanding of the cosmos, inviting profound questions about the very fabric of reality and the potential for interactions we have yet to observe. Early investigations into forces emerged from classical mechanics and electromagnetism, with Newton and Maxwell laying foundational frameworks. The 20th century revealed the strong and weak nuclear forces, yet discrepancies in galactic rotation curves and cosmic acceleration suggested hidden dynamics. Scientists like Fritz Zwicky, Vera Rubin, and later theoretical physicists proposed the possibility of unseen forces influencing matter on both cosmic and subatomic scales. Unknown fundamental forces may involve subtle interactions beyond the standard model, potentially mediated by hypothetical particles or fields. Concepts like fifth forces, scalar fields, or modifications to gravity offer theoretical scaffolding. These forces could manifest as deviations in gravitational behavior, anomalous particle interactions, or unexplained energy distributions, linking observed phenomena to deeper laws. Current theories span modifications of Newtonian dynamics, extensions of general relativity, and quantum field hypotheses. Competing frameworks explore both long-range and short-range interactions, employing rigorous mathematical models to predict observable effects. Experiments from precision torsion balances to cosmological surveys aim to detect minute deviations, while some anomalies in dark matter distribution or neutrino behavior hint at unknown interactions. challenges persist as current observations provide indirect evidence with significant uncertainties. Paradoxes, such as the dark energy problem and unexplained galactic motions, fuel ongoing inquiry. Connections to dark matter, dark energy, and unification theories suggest that discovering new forces could redefine physics. Future endeavors include advanced particle accelerators, space-based observatories, and refined computational simulations. A breakthrough could illuminate hidden symmetries of nature, revolutionizing our understanding of reality. The pursuit of unknown fundamental forces underscores the limits of human knowledge, urging a deeper exploration of the universe's hidden dynamics and the mysteries that remain tantalizingly beyond reach. 3 generations of particles. The universe is built upon a foundation of fundamental particles organized into 3 distinct generations. These particles, quarks and leptons, form the very matter and forces that govern the cosmos. Understanding why particles exist in 3 generations is central to modern physics, touching on questions of symmetry, matter-antimatter asymmetry, and the underlying structure of reality itself. Despite extensive study, the reason for this tripartite pattern remains an enduring mystery. The exploration of particle generations traces back to early 20th century discoveries of the electron, proton, and neutron. Later, the muon and tau leptons, along with their corresponding neutrinos and heavier quarks, revealed the layered complexity of matter. Pioneering experiments at CERN, Fermilab, and other accelerators, along with contributions from physicists such as Murray Gell-Mann and Sheldon Glashow, shaped our evolving understanding of particle families and the Standard Model framework. Particles are classified by mass, charge, and interactions, with each generation heavier and less stable than the previous. Quarks combine to form protons, neutrons, and mesons, while leptons, such as electrons and neutrinos, participate in weak and electromagnetic interactions. Flavor oscillations, neutrino mixing, and CP violation highlight the intricate physics connecting generations. The Standard Model offers a robust framework, but leaves fundamental questions unresolved. Alternative theories such as supersymmetry, grand unification, and string-inspired models attempt to explain the pattern mathematically and conceptually. Experimental evidence from particle colliders, neutrino observatories, and cosmic background studies provides strong support, though anomalies like neutrino mass hierarchy and rare decay processes persist. Understanding 3 generations connects to broader physics, matter-antimatter imbalance, dark matter candidates, and cosmological evolution. Future facilities, including high-luminosity colliders and precision neutrino experiments, promise deeper insight. The quest to explain particle generations not only advances fundamental science, but invites philosophical reflection on the structure and origin of the universe, sustaining curiosity and the pursuit of knowledge. Neutrino mass. Neutrinos, elusive subatomic particles, challenge our understanding of the universe with their almost imperceptible mass. Though once considered massless, their subtle influence shapes fundamental physics, from particle interactions to the evolution of galaxies. Determining their mass is crucial for unraveling the dynamics of the cosmos and addressing the deep mysteries of matter and energy. Early studies of beta decay hinted at the existence of neutrinos, with Wolfgang Pauli proposing them to conserve energy and momentum. Subsequent experiments by Clyde Cowan and Frederick Raines confirmed their presence, sparking decades of investigation into their properties. Over time, the notion of massless neutrinos was contested, particularly with the discovery of neutrino oscillations, revealing their ability to change flavor of phenomenon, implying non-zero mass. Neutrino mass intertwines with concepts like flavor oscillation, weak interactions, and the standard model of particle physics. These particles interact via the weak nuclear force, rarely colliding with matter, yet their behavior profoundly impacts astrophysical processes, including supernova dynamics and cosmic background evolution. The tiny mass differentiates neutrinos from photons, subtly affecting the structure of the universe. Current theoretical frameworks explore neutrino mass through Dirac and Majorana formulations, each proposing distinct mechanisms and symmetries. Models involve intricate matrix representations, such as the PMNS matrix, capturing oscillation probabilities and mass hierarchy. Competing hypotheses question the absolute scale of mass and the potential existence of sterile neutrinos, extending beyond known interactions. Empirical evidence arises from oscillation experiments, including superkamiokande and SNO, and cosmological observations, like the cosmic microwave background. These findings constrain mass differences, yet the absolute mass remains elusive. Occasional anomalies provoke reconsideration of established models. Challenges include reconciling neutrino mass with the standard model and understanding their role in dark matter. Connections extend to lepton number violation, early universe physics, and the matter-antimatter asymmetry. Future initiatives, such as KATRIN and next-generation neutrino observatories, aim to pin down mass with unprecedented precision. Unveiling this property may redefine particle physics and cosmology, bridging fundamental gaps in our knowledge, inspiring profound reflection on the universe's subtle yet decisive mechanisms. Sterile neutrinos. Sterile neutrinos represent a hypothesized extension to the standard model of particle physics, particles that interact exclusively via gravity and not through the weak nuclear force. Their existence could profoundly reshape our understanding of the universe, offering potential explanations for dark matter, the matter-antimatter asymmetry, and anomalies in neutrino oscillation experiments. Despite their theoretical appeal, sterile neutrinos remain elusive, their properties and even existence posing a tantalizing enigma for physicists and cosmologists alike. The concept traces back to the mid-20th century as physicists sought to account for missing mass in the universe and discrepancies in neutrino detection. Early neutrino research by Wolfgang Pauli, Enrico Fermi, and later experiments at Los Alamos and superkamiokande laid the groundwork for recognizing neutrino oscillations. Over decades, the notion of a sterile variant emerged as an elegant solution to anomalies in solar, atmospheric, and reactor neutrino experiments. Sterile neutrinos are defined as neutrinos that do not couple to the weak interaction, distinguishing them from the familiar electron, muon, and tau neutrinos. Their dynamics are governed by mass mixing, with active neutrinos permitting oscillations that can subtly affect experimental observations without direct detection. These particles are deeply intertwined with phenomena like leptogenesis, neutrino oscillation patterns, and cosmic structure formation. Current theoretical frameworks range from minimal extensions of the standard model to elaborate seesaw mechanisms, each predicting different masses and mixing angles. Competing hypotheses contend with whether sterile neutrinos constitute dark matter or represent a distinct sector influencing cosmology. Observational evidence remains inconclusive, with anomalies in LSND, mini-Bueni, and reactor neutrino experiments hinting at their presence, yet conflicting with constraints from cosmology and other neutrino experiments. Key challenges include reconciling inconsistent data, determining precise masses and mixing, and confirming existence without direct interaction. The search intersects with broader questions of dark matter, the evolution of the early universe, and unification of forces. Upcoming experiments, such as DUNE, KATRIN, and precision cosmological surveys, aim to probe these possibilities, potentially offering transformative insights. The pursuit of sterile neutrinos encapsulates both the rigor of particle physics and the philosophical wonder of uncovering hidden constituents of reality, ensuring the journey continues at the frontier of knowledge. Supersymmetry. Supersymmetry, often abbreviated as SUSY, is a proposed extension of the standard model of particle physics that suggests every fundamental particle has a yet undiscovered partner, differing by half a unit of spin. Its significance lies in its potential to resolve persistent enigmas in physics and cosmology, such as the hierarchy problem, dark matter composition, and unification of forces. Despite decades of research, supersymmetry remains unobserved, leaving a profound mystery at the heart of theoretical physics. The concept emerged in the early 1970s with pioneering work by Yuri Golfand, Evgeny Likhatman, and Julius Wess. These ideas, built upon quantum field theory, proposing symmetry between fermions and bosons. Over time, supersymmetry evolved from a purely mathematical construct to a central candidate in high-energy physics, influencing theories of grand unification and string theory. At its core, supersymmetry introduces superpartners, fermions paired with bosons and vice versa. These hypothetical particles, such as squarks and leptons, obey new symmetry transformations that extend conventional spacetime symmetries. The framework predicts cancellations of quantum corrections, offering a solution to the immense disparity between gravitational and electroweak scales. Related phenomena include potential dark matter candidates, like neutrinos and modified Higgs boson behaviors. Theoretical models vary, ranging from minimal supersymmetric extensions of the standard model to complex string-inspired frameworks. Competing hypotheses include alternative explanations for dark matter and naturalness problems, emphasizing different mathematical formulations and symmetry-breaking mechanisms. Evidence remains elusive. Particle accelerators, notably the Large Hadron Collider, have yet to detect superpartners, challenging model parameters. Observational anomalies in cosmic rays and dark matter distribution offer tantalizing but inconclusive hints. Current challenges involve fine-tuning, large parameter spaces, and reconciliation, with experimental null results. Research explores higher energy collisions, precision measurements, and refined theoretical constructs. Supersymmetry intersects with cosmology, quantum gravity, and dark matter research. A confirmed discovery could revolutionize understanding of the universe's fundamental structure. Future prospects include next-generation colliders, advanced detection methods, and theoretical breakthroughs in unified field theories. Solving supersymmetry could illuminate dark matter, unify forces, and deepen comprehension of spacetime itself. In conclusion, supersymmetry remains a profound theoretical frontier. Its potential to answer fundamental questions is immense, yet the absence of empirical confirmation preserves a horizon of mystery, inspiring ongoing exploration in the quest to decipher nature's deepest symmetries. True vacuum state. The true vacuum state represents the lowest possible energy configuration of a quantum field, a concept central to understanding the stability and evolution of the universe. Its significance in physics lies in its implications for cosmology, particle physics, and the fate of the cosmos, particularly regarding the potential metastability of our current vacuum. Despite decades of study, whether our universe resides in a true or false vacuum remains an open and profound question. Historically, the notion of vacuum evolved from classical emptiness to a dynamic quantum entity. Early quantum field theories, influenced by Dirac and Heisenberg, suggested that even empty space harbors fluctuating energy. The discovery of spontaneous symmetry breaking and the Higgs mechanism provided the first concrete framework for considering vacuum states as physically meaningful, with contributions from scientists like Niels Bohr, Peter Higgs, and Murray Gell-Mann. Core concepts include the distinction between false and true vacuum, quantum tunneling, and vacuum decay. The true vacuum corresponds to the absolute minimum of the potential energy, while metastable false vacua can persist for eons. Quantum fluctuations may trigger transitions between these states, potentially releasing catastrophic energy, a process intricately linked to early universe inflation and cosmological phase transitions. Current theories explore these ideas through the standard model of particle physics and beyond, including string theory landscapes and multiverse hypotheses. Mathematical approaches often involve potential energy diagrams, instantons, and vacuum expectation values, highlighting competing models for vacuum stability. Observational evidence is indirect, inferred from the Higgs boson mass, cosmic microwave background measurements, and the apparent longevity of our universe. Anomalies, such as the cosmological constant problem, challenge current understanding. Open questions include the true vacuum's energy scale, its decay probability, and its role in dark energy. Connections span inflationary cosmology, particle physics, and quantum gravity, with far-reaching implications for the ultimate fate of the cosmos. Future prospects involve precision measurements of fundamental constants, advanced collider experiments, and refined theoretical models that may illuminate the true nature of vacuum stability, bridging profound mysteries in physics. Proton decay. Proton decay represents a profound question at the heart of particle physics and cosmology, probing the very stability of matter. Understanding whether protons, the building blocks of atomic nuclei, can spontaneously disintegrate, challenges our conception of the universe's longevity and informs grand unified theories. Its significance extends to explaining the asymmetry between matter and antimatter and the ultimate fate of all matter. Early concepts of proton instability emerged with the development of quantum field theory and the search for grand unification. Pioneering physicists, including Georgi, Glashow, and Sakurai, proposed mechanisms predicting decay channels, while experiments in the 1980s, such as those at Kamiokande and IMB detectors, sought empirical verification. Over decades, the absence of observed decays refined theoretical constraints, shaping modern particle physics. Proton decay is theorized as a process in which a proton transforms into lighter subatomic particles, such as positrons and neutral mesons, mediated by hypothetical heavy bosons. This violates baryon number conservation, a principle long considered sacrosanct and links to broader phenomena like neutron decay and lepton generation. Theoretical frameworks include minimal SU5 and SO10 grand unified theories predicting specific lifetimes and decay modes. Alternative hypotheses explore supersymmetric models or extra-dimensional mechanisms, often expressed through complex Lagrangians and decay amplitude calculations. Experimental evidence remains elusive, with current detectors setting lower bounds on proton lifetimes exceeding 10 circumflex 34 years. Some anomalies in neutrino and cosmic ray observations hint at new physics, but are inconclusive. The primary challenges involve reconciling theoretical predictions with non-detection and understanding possible suppression mechanisms. Proton decay intersects with dark matter studies, baryogenesis, and cosmic evolution. Confirmation could revolutionize our grasp of fundamental forces and the ultimate destiny of matter. Future prospects include hypercamiocand and Dune experiments, advancing both observational sensitivity and theoretical refinement. Resolving proton decay's mystery promises transformative insights into the universe's deepest laws, fueling curiosity and pushing the boundaries of scientific imagination. Success of the Standard Model. The Standard Model stands as one of the crowning achievements of modern physics, providing a remarkably accurate framework for understanding the fundamental particles and forces that compose the universe. Its significance lies not only in unifying electromagnetic weak and strong interactions, but also in enabling precise predictions that experimental physics consistently validates. Despite its success, profound mysteries remain, such as the nature of dark matter and the incorporation of gravity into a quantum framework. The roots of the Standard Model trace back to early 20th century discoveries in quantum mechanics and particle physics. Pioneering experiments including Rutherford's scattering studies and the identification of the electron laid the groundwork, while theorists such as Dirac, Fermi, and Yang-Mills formulated the mathematical structures that underpin particle interactions. Over decades, the understanding of quarks, leptons, and gauge bosons evolved, culminating in the comprehensive framework recognized today. Central to the Standard Model are concepts such as quantum fields, gauge symmetry, and spontaneous symmetry breaking. Particles are excitations of underlying fields, and interactions are mediated by force-carrying bosons, with the Higgs mechanism providing mass to fundamental particles. Phenomena like particle decay, scattering processes, and CP violation exemplify the model's predictive power. Current theories extend the Standard Model by exploring supersymmetry, grand unified theories, and potential connections to quantum gravity. Mathematical formalisms like Lagrangians and Feynman diagrams enable precise calculations, while competing hypotheses aim to address phenomena beyond its reach. Experimental evidence abounds. Collider data, precision measurements of particle masses, and observations of weak decays all confirm the model. Yet anomalies such as neutrino oscillations and the muon G2 discrepancy hint at physics beyond the current paradigm. Challenges include the absence of a quantum description of gravity and unanswered questions about matter-antimatter asymmetry. Research continues in high-energy experiments and cosmological observations, linking the Standard Model to dark matter, dark energy, and the early universe. Future prospects involve next-generation colliders, precision neutrino experiments, and theoretical advancements in unification frameworks. These efforts may reveal deeper layers of reality, potentially reshaping our understanding of the cosmos. The Standard Model exemplifies human ingenuity in deciphering nature's blueprint, offering profound insights, while reminding us of the universe's enduring mysteries, inviting curiosity and exploration. Physics beyond the Standard Model. The Standard Model of particle physics has provided an astonishingly accurate framework for understanding the fundamental particles and forces in our universe. Yet it remains incomplete, unable to explain dark matter, dark energy, neutrino masses, or the matter-antimatter asymmetry. These unresolved mysteries drive physicists to explore physics beyond the standard model, seeking a deeper, more unified description of nature. Historically, the quest for physics beyond known frameworks began with the recognition of phenomena that the standard model could not accommodate. Early discoveries, such as neutrino oscillations and the Higgs boson, hinted at hidden layers of complexity. Pioneering scientists like Wolfgang Pauli, Murray Gell-Mann, and Sheldon Glashow laid the groundwork for theoretical expansions, while experiments at CERN and other laboratories continuously refined our understanding. Core concepts in this field include supersymmetry, extra dimensions, grand unified theories, and string theory. Supersymmetry posits partner particles for every known particle potentially explaining dark matter. Extra-dimensional theories suggest that hidden spatial dimensions could reconcile gravity with quantum mechanics. These frameworks explore phenomena like proton decay, lepton flavor violation, and vacuum stability. Current models propose a spectrum of competing ideas from minimal supersymmetric extensions to complex string-theoretic landscapes. Approaches vary between highly mathematical formulations and phenomenological models that can be tested experimentally. Observational evidence includes collider data, cosmic microwave background measurements, and neutrino experiments, revealing tantalizing hints, but no definitive breakthroughs. Certain anomalies, such as the muon G2 discrepancy, challenge existing theories and inspire new proposals. Significant challenges remain: reconciling quantum mechanics with general relativity, understanding dark energy, and probing energy scales beyond current technology. Connections to cosmology, black hole physics, and early universe conditions underscore the interdisciplinary impact. Future prospects include next-generation colliders, gravitational wave observatories, and advanced theoretical simulations, promising potential revolutionary insights. Physics beyond the standard model embodies the frontier of human curiosity, where each unanswered question may reshape our understanding of reality itself.